The main project of this video is to learn how to take derivatives of exponential functions of the form b to the x, where b is just some arbitrary base for the exponential. But to get there, we need to quickly review what we accomplished in the previous video. So what we did in the previous video is we set out on a quest to solve this simple differential equation y prime equals y. In other words, we were looking for functions that are equal to their own derivative. And as it turns out, a solution to that is y equals e to the x. And we figured out that special number e, also called Euler's number, is the limit as h goes to 0 of 1 plus h to the 1 over h power. And for what it's worth, the decimal approximation is about 2.71828, but we usually just call it e. So the takeaway here is that e to the x is the special function where if we take its derivative, we just get back the same function. So the derivative of e to the x is e to the x. Now we also generalized our result a little bit, and we took a look at the differential equation y prime equals k times y. So if I take the derivative of a function, I get k times the original function. And as it turns out, the solutions to this equation are just a slight modification of e to the x. It's just y equals e to the kx. Now the reason why this is true is that when we take the derivative of e to the kx, we have to view that as a function composition. It's e raised to some function kx. So we apply the chain rule to the derivative here. We take the derivative with respect to kx, and that gives us the exponential piece here. The derivative of e to the kx with respect to kx is just e to the kx, but then the chain rule kicks in. And the chain rule says we have to take the derivative of the inner function and tack on that factor. So the derivative of kx is just k, so that's tacked on out in front. Now what we're looking at is k times the original function. So that means e to the kx satisfies the equation y prime equals k times y. So there's the derivative of a natural exponential function combined with the chain rule. Now the main project of this video is to figure out how to take derivatives of functions like this. Y equals b to the x. So here's how we get it done. What we're going to do is exploit the fact that we already know how to take derivatives of functions like e to the kx. So we can re-express this exponential b to the x in terms of a natural exponential. So we're going to rewrite that as e to the natural log of b to the x. Now the reason this is possible is because e to the x and natural log x are inverse functions of each other. So when we compose them, they undo each other. So this is true for any expression, not just b to the x. If I take e to the natural log of something, it's exactly the same as that thing. So next we're going to apply log properties to pull a factor of x out of the exponent there, and we can rewrite this as e to the natural log b times x. Now we're ready to take the derivative because this is in the form e to the kx, and we have some experience with functions like that. Remember, the first part of the chain rule just gives us an e to the natural log b times x, but then we have to multiply by the derivative of natural log b times x, which is simply natural log of b. Now our final step here is to rewrite e to the natural log of b multiplied by x back in its original form. Remember, that was simply b to the x. So that's what happens when we differentiate an arbitrary exponential function. We just get back the original function, but multiplied by the natural log of the base. And I want to point out that this is a pretty similar behavior to what happens with the natural exponential. When you differentiate the natural exponential e to the x, you just get back the original function e to the x. When you differentiate the function b to the x, the behavior is almost the same. We get back b to the x, but there's a slight adjustment here where we have to tack on a factor of natural log b. So let's wrap it up with a few examples. Our first example is a straightforward application of our new formula. We just have a base of b here. So when I take the derivative of 3 to the x, I get natural log of 3 multiplied by 3 to the x, and that's it. In our next example, we're differentiating e to the sine x. So we're dealing with a natural exponential function here, but it's a function composition and we have to apply the chain rule. So I start out by taking the derivative of e to the sine x with respect to sine x. That's just e to the sine x. In other words, we treat sine x like a single variable for the moment, and we just take the naive derivative of that thing. So the derivative of e to the variable is just e to that variable. Now the chain rule says we have to tack on the derivative of that inner function sine x. So that gives us a factor of cosine x. It's probably a little nicer to write the cosine x in front. So we get a final answer of cosine x e to the sine x. Now in our final example, we have a non-standard base of 5, but we also have to use the chain rule here. So I differentiate 5 to the 3x with respect to 3x, just treating 3x like a single variable for the moment. And I know this gives me natural log of 5 times 5 to the 3x, the original exponential function. The chain rule then says we have to tack on the derivative of that exponent, and that's just a 3. So cleaning things up a little bit, we write this as 3 times the natural log of 5 times 5 to the 3x, and we're done. In the next video, we use implicit differentiation to figure out how to find the derivative of the natural log function. And then we'll work a variety of examples, including combinations with the chain rule. I'll post a link to that video at the upper left, and I'll see you there.